So today we're going to be looking at this mosquito repelling plug-in device that I picked up at the local Kaufland. So this isn't your typical blue pesticide dispensing anti-sea heater like you've seen before. This is actually a audio-based repellent that I can say off the bat probably doesn't work at all. But as it says here in German, this is a device that emits tones between 3,000 and 20,000 hertz. It doesn't emit any chemicals, and it operates on standard grid voltage using less than half a watt. So let's get into this box. This thing sells for less than €2, so super cheap. Inside we have the usual useless paper warnings. We can throw that off to the side. And we are left with this very basic and nondescript plug-in device. You can see it plugs in. The LED lights, I can barely hear some kind of sub-audible tone. Not sure if you can hear that. So it just chirps around and nothing really happens. So let's take this apart. They've very kindly given us 2 screws. So that makes disassembly that much easier. Feels very light, so there's not going to be much in here. Just a circuit board with some kind of either capacitor or resistive dropper and some type of speaker. So we're in like Flynn. Top comes off. We have this simple circuit board. So yeah, here we have the piezo crystal buzzer, one slightly bigger resistor. This is probably the dropper resistor, and the indicator LED. So let's make sure, okay, any capacitors are discharged. And here we have the very simple circuit board. So we have the microcontroller here, the single wave rectification diode coming off the incoming supply. This is the LED. We have this diode, which is going to be a Zener diode that's going to clamp the supply voltage to the chip. And then here in back, we have our half watt resistor that's going to be dropping most of the rest of the current here. So very simple circuit, nothing too interesting going on here. Obviously, we have our piezo buzzer connected here, so obviously the chip is regulating the output over the buzzer with a current limiting, looks like 15K tiny 8th watt resistor there. So nothing much to see here. We're going to bring in the schematic that I've managed to draw up by the magic of putting things back together again and then taking them apart in dubious excitement fashion. So here we can see the fairly simple circuit. So we have our 220 AC coming in, rectified through our diode. There's an LED in series there too. There's our 2 capacitors that do some stabilization. And we have our Zener diode that is here that I actually unsoldered and measured. This is somewhere around a 5 volt Zener diode. This connects to the MCU, so we have our power and ground. So basically the whole power rail in this system, this is plus 5 volts up here, and this is the 0 volt rail. Then we have this 100K half watt resistor that we can see on the bottom of the board here. It's actually doing the job of a resistive dropper, so it's dropping most of the line voltage over it. And then we have on the single output of the microcontroller, we have the 15K 8th watt resistor going to the piezo buzzer. So all in all, a very simple system. Nice simple way of generating a 5 volt supply off of mains voltage. very cheap and simple single wave rectification. They could have used a capacitive dropper, but seeing that this circuit uses so little power in the 2 or 3 milliamp range, a resistive dropper is perfectly fine, and this resistor here probably isn't even going to get very warm. So doing a little bit of further probing with the oscilloscope, I managed to figure out the control logic of the chip. So basically the only thing it does is generate 17 different tones, each for 2 seconds duration, going from 2.6 kilohertz to 17.8 kilohertz, and it just loops around doing its little buzzing. So if we can shoddily put this back together, maybe inverted like this, I can show you one of the pitfalls you will encounter when you try and measure these mains single phase single wave rectified devices. That you will have quite some difficulty actually getting accurate measurements from your multimeter from measuring them. So over this M7 diode here, we'd expect to have our 0.7 volt drop when it's running. So we have our input here, which would be the positive, and this here on the cathode of the diode should be at 0.7. So if we gingerly turn this on and very carefully insert our probes, we can see that we're getting minus 85 volts. So this is quite strange. And if we go over to, let's say, the resistive dropper, our, what was that, 100K resistor, and if we measure that, we can see that it's dropping 103 volts. Well, that doesn't make much sense. Or if I get the polarity right here, so we can see, okay, so that thing's dropping 103 volts, when realistically it should be dropping 200 and some volts. And our diode here is, that should be dropping 0.7 volts, is dropping minus 85 or something. So this is actually one of the pitfalls you will find when trying to probe a single wave rectified device with your standard multimeter. So what happens here is that your multimeter is basically giving you an average voltage that it measures over some microseconds or even milliseconds, and averages that out. So it isn't giving you the peak voltage that it measures. So over this rectification diode, during one half cycle, it's going to be 0.7 volts. On the other half of the cycle, it's going to be at negative mains voltage. So the multimeter here, as you can see, it's basically doing an average measurement over a number of cycles, and it's coming up with minus 80 volts, so actually positive on the right, negative on the left, giving us minus 80 volts over the diode, and giving us 100 and some volts over this resistor, even though we know this is going to be somewhere in the region of 300 plus volts, since European mains should be somewhere around 335 volts. DC rectified, that's coming off of 235 volts AC RMS. So I'm going to show you some of my oscilloscope measurements right now. So first, we can have a look at the picture we get probing our diode. So you can see here that we have our 0.7 volt pulses in the forward conducting rectifying regime, and then in the other half cycle it drops down to the negative mains voltage. Further, we have our LED that again shows this behavior, so 1.9 volts forward conducting on its rectified half cycle when it's on, and it doesn't go that far down, so it goes to minus 2.6 volts actually on the other half cycle. And that's actually quite interesting, since on the non-rectified half cycle you actually have lower voltage here than at these capacitors that are holding a positive charge. So you have that inversion of polarity at the LED during one of the half cycles. Going further, we can take a look at the wave picture of the Zener. As we expect there, it's on the rectified half cycle, it's giving us 5.4 volts, and then the rail slowly drifts down to 3.6 volts. That's carried by the capacitors that are keeping the rail powered and stable. So it never drops down lower than 3.6 volts. And finally, we can have a look at the waveform of the resistor. So here we have the very typical pulses of mains voltage when the rectifier, the diode, is working. So we have the rectification where that 100K resistor is carrying almost mains voltage minus the voltage of the circuit. So here it's carrying 226 volts, while the rest of the circuit is about 8 volts. And on the other half cycle, it is at 0 since the diode is not conducting. So all in all, the numbers actually add up quite well. Going from the crazy multimeter measurements of minus 80 volts on the rectifying diode and 103 or 110 volts on the resistive dropper, when we actually look at this very simple device with the oscilloscope, the numbers actually add up quite nicely. So we have our 5.4 volts on the Zener, 1.9 on the LED, 0.7 volts on the rectifying diode, and that leaves another 326 on the resistive dropper, and that makes up our 335 volts rectified mains very nicely. One last interesting thing that you might discover in these nondescript chips you might find. We can see here there's absolutely no marking on this chip, but I actually unsoldered it, and surprisingly enough, on the bottom of the chip there was a laser etched number and model that of course gave no results Googling it, but nevertheless, in some cases you might actually discover the identity of your chip by looking at the bottom side. So thank you again for watching this very simple and intriguing device. I'll put in, you'll see now the waveforms of the tones it produces. And I hope you'll come again and watch our next teardown and reverse engineering effort. Thank you for watching. See you next time. Bye-bye.